video, we want to review Rapid Spanning Tree Protocol, which we covered back in your CCNA studies. And remember, Cisco's specific implementation of Rapid Spanning Tree Protocol is called Rapid PVST+, because Cisco's PVST+, which allows us to have a different instance of spanning tree for every VLAN, it's going to be used as the basis for Rapid PVST+. But the convergence can happen quicker because of the rapidness of Rapid PVST+. Now let's review some of the basics of Rapid Spanning Tree Protocol. We still have a root bridge, just like we do in traditional Spanning Tree Protocol. We still have designated ports, which is a port on a segment that's closest to the root in terms of cost. We still have a root port, which is a port on a non-root bridge that's the closest to the root in terms of cost. We still have a disabled or port that is shut down. However, we have a couple of different types of blocking ports. We have an alternate port and we have a backup port. Let's make sure we understand the difference between those. Take a look at that link between SW2 and SW3. Notice the end on SW2 is a blocking port, but it's an alternate port, whereas the link on the right-hand side of SW3 going up to the hub, that's also a blocking port, but it's a backup port. The difference is we're connecting to a hub with the backup port, and we're connecting to a switch with the alternate port. You see, if we just connected two ports from a switch into a hub, we're going to have a layer 2 loop. That traffic is just going to come through the hub and right back into the other port. We don't want that. So we need to block one of those ports. But if we're going to a hub, a shared media device, that's called a backup port. But if we're going into a switch, which is probably about 100% of the time these days, that's going to be called an alternate port. Let's also define some of the different port states. Remember, with traditional spanning tree protocol, we had the blocking, listening, learning, forwarding. Well, here, instead of blocking, we talk about discarding, which is the same as blocking. We're going to be dropping data packets. And we're going to be doing that if we're in the alternate state, connecting into a blocking port on a switch, in the backup state, connecting into a hub, or a port that's administratively shut down or disabled. And instead of having a listening and learning state, those have been combined into a single learning state that we're going to transition through. And finally, we go to the forwarding state, where we're actively forwarding traffic. And one way that convergence happens quicker is that we don't rely on the root to just stop sending BPDUs. And after a while, we get suspicious thinking that, it's been a while since I heard from the root. I wonder if something is up. Well, what we're going to do instead is allow everybody in the topology to play a role in updating everybody else. When there is a change in the topology, when a switch notices that a link goes down, any of our switches, be it a root bridge or not, can send out a topology change notification, or a TCN. That can help speed up the convergence process. A couple of other terms I want you to be aware of before we get into the configuration in the next video. We have different link types. And if we're just connecting from a switch into another switch and we're running it full duplex, that's a point-to-point type of connection. That's a point-to-point link type specifically. If we're connecting into a hub, which is a shared media device, well, that's going to be a shared link type. And remember, if we're connecting into a hub, that's going to be running at half duplex because we have to run CSMA CD on a hub. And if we're connecting into an end device like a PC or a laptop here, that's going to be an edge port. Now, this brings up a point of confusion. It seems like that's a full duplex port from the perspective of switch SW2. Yes, it's connecting to a laptop, which is an edge device, but how does it know it's not connecting to a switch? Shouldn't that be a point-to-point link type? Well, actually, it is a point-to-point link type, but it's a special type of port on that point-to-point link type. It's an edge port. How do we make that port an edge port? We configure something we talked about in our CCNA studies called port fast. Port fast is when we go into a switch port and we say, I know that you want to run through the normal delays of spanning tree protocol to make sure that we're not forming a loop before you go active on this port, but I promise I'm not going to connect another switch to this port. It's going to be some sort of an end device. You will never see a bridge protocol data unit come in on this port. So please don't make me wait through the delay of spanning tree protocol. And once we give that solemn vow and we say, trust me, go active almost immediately, and we enable port fast, then we don't have to wait for the 30 seconds that we would normally wait with traditional spanning tree protocol when we plug in an end device. Well, if we enable port fast here, that makes this an edge port. Now let's take a closer look at how all the different switches participate together to inform one another about a new topology once we lose our current root bridge. Let's say that before the transition happened, before there was a topology change, let's say that the root bridge used to live somewhere off the bottom of the screen. However, something happened to that root bridge. It went down, and now we'll say that the root bridge is somewhere off of the top of the screen. And as a result, switch SW1 has a new root port. That's step one in this process. We've got a new root port, which is a port on a non-root bridge that's closest to the root in terms of cost. You see, the bottom port on switch SW1, that used to be the root port because it would go out of the bottom to get to the root bridge somewhere off the bottom of the screen, but now it's going to go out that top port. Well, as a second step, once it elects a new root port, what's it do with the other root port? Well, that root port, just to prevent any sort of temporary loop, is going to go into a blocking state. So it's going to block. That's going to be step 2. And we want to proactively inform switch 2 about this change. So what we're going to do, step 3, is we send out a proposal. And this proposal says, I propose that I know a better way to get to the root bridge. Our other root bridge is no longer available via the path you used to use. Now I'm the best way to get to the root. And if switch 2 believes that, if it accepts it, it will send out an agreement. That's going to be step number 4. We'll say, okay, I'll agree to that. And when it agrees, it takes the port which was previously a designated port, because that was the end on the segment that was closest to the root in terms of cost when the root was off the bottom of the screen. So step number 5 is we're going to transition from a designated port to a root port on the top of switch SW2. That is step number 5. But switch SW1 still has a blocking state on its bottom port. But as soon as it receives that agreement message, about the same time that step number 5 is happening, step number 6 happens. We transition from a blocking state and we become a designated port. Now on that segment between SW1 and SW2, the bottom port on SW1 is the closest to the root. That is step number 6. Now, I'll not go through all those steps again, but you can see the same kind of thing is going to happen between switch SW2 and SW3. We'll go blocking on this bottom port. We'll send the proposal. We'll get the agreement, and it'll daisy chain like that throughout the rest of the tree. And that's a review of how Rappid Spanning Tree Protocol works. Now, join me in our next video where we're going to take a look at the configuration of Rappid Spanning Tree.